So I'm here to show you the sun angle calculations for any passive solar building, including greenhouses, houses, shops, barns, chicken coops, whatever you're building. If you're in the northern hemisphere, the sun is to the south. When the sun is lowest, it's cold outside and you want that to pick up that energy. When the sun is high outside, that means it's hot and you want to protect your building from that hot sun heat. If you are in the northern hemisphere and have a building that is literally facing south, you are smarter than 99% of the general public. For some reason, this isn't common knowledge, but I'm an expert at it to optimize your building, and we can reduce your heating and cooling needs in a building by up to 100%. On a new construction build like a house, the cost to build this thing is $0. Let me show you. So if this is somehow new to you, I have to just give you a general explanation of how the sun and the earth works. So if you're in the northern hemisphere, so Canada especially, but the United States as well, the sun is south. This is south, okay? The sun is always south. In the summertime, the sun is higher, and in the wintertime, the sun is lower. When it's cold outside, that's when you're trying to pick up the sun. When it's hot outside, that's when you're trying to protect your buildings from the sun. So you can find out, you need to know some information. Wherever your location is on the planet, you need to know your longitude and latitude. So for me, I am 52 degrees north. So what is that? That means on planet Earth, the big ball that we live on, where are you? And I'm at 52 degrees north. Okay, with that information, I can find out my sun angle on any given day, like at solar noon. But two of the most important dates are called the solstices. So on December 21st is the winter solstice, and for me at latitude 53, my sun angle is at 14 degrees above elevation. So this is 0, 14 degrees, so a very steep angle. My summer solstice is June the 21st, and that angle is at a 61 degree angle on June 21st. So that's our hottest time of the year when it's hot outside, and most houses need air conditioning. So you look up your latitude. I'll put the links to the app that I like to use where you can find all of this information. Now, after you know that, those are some constants that we have in our formulas, okay? Knowing your sun angles and where the sun is, the coldest and the warmest time of day. You can also calculate it for anything in between. The next thing you need to know is some basic trigonometry using right angle triangles. So trigonometry, you need a few constant in here. So on a right angle triangle, we know 90 degrees. Then you need to know another angle. And from that, all the angles on a right angle triangle equal 180 degrees. Then you need to know a side of your right angle triangle. And from that, you can find out all other essentially values of that triangle, all the angles and all the sides, using sin, cos, and tan functions of a triangle. So sin is opposite over hypotenuse. So if this is the angle we're working with, this would be opposite, adjacent, and hypotenuse is the opposite from the right angle triangle. Cos is adjacent over hypotenuse, but we're going to specifically use the tan function for all of our formulas today. Tan function is opposite over adjacent. So here's a diagram of my house that I built for myself with my two hands, and I designed it myself. It's designed perfectly as a passive solar house. My house is 9-foot ceilings. This is south. My trusses, after I did these calculations, I had them structurally engineered at the truss factory for the load point to be exactly over my wall. And here is an example of the sun in my house. 14 degrees, the sun's coming in, and I'm getting full sun in my entire window on the south of my building. Here's the summer sun, the summer solstice. It's not even touching my building, but I also calculated at what day is my window completely shaded from any sun coming in. So what you get, you have to find out where your triangles are that you're dealing with. So in this case, this is a triangle, a right angle triangle right there. So this is, we're going to calculate for the winter solstice sun. Now, we have a right angle triangle, so 90 degrees, and we also have the winter solstice angle of 14 degrees, so we know our angles. But in order to find out our overhang of what we need, our eave overhang on the house or any building, we need to know one constant side. Okay, so what is my constant on this? Well, my trusses go this way, and you have glazing, and I have a structural beam above the window. So there's a constant that we have. 12 inches is my beam above the window. So let's input 12 inches, and this is how you calculate it. Tan 14 degrees is equal to opposite over adjacent. Opposite over adjacent. So 12 inches over, we're trying to find X, the eave overhang. So if you don't have a scientific calculator, I'll put a link to a simple one that I like to use. But you plug it in, tan 14 degrees, and that's all you plug in the scientific calculator. It's going to pop you out a value, and that for me is 0.2493. So tan 14 is equal to 0.2493. That equals 12 inches over X. We're trying to find X. X is equal to 12 over that. X is equal to 48 inches. 48 inches is our overhang to get the full winter sun, when the sun is lowest in the sky, into our glazing. Okay, so we kind of figured that out. That works for the winter. What about the summertime? Well, now that we know if we're going to do a 48-inch overhang, we have that as a constant. And let's try to figure out where the bottom of our window is on our structure. So for me, it's 12-inch beam overhang, and then the window starts right there, nice and convenient. My house, I did a 9-foot wall for a reason, like me guessing and checking and calculating. My house is also a smaller house, and I had to deal with functionality issues as well. So below the window, I wanted 36 inches. So on one of my south windows, I have a countertop. 36 is countertop height. And then another one, I have the back of a piece of furniture, right? A couch. And I don't want glazing behind that. It's kind of going to give you frost issues and condensation issues in the winter and things. So there, you have to deal with function as well. But, so 36, we know that in here. So let's do a window that's 60 inches in a 9-foot wall. So from the eave to the bottom of the window, we've got 72 inches. A 60-inch window plus a 12-foot overhang, 72 inches. So what we know now is 48-inch overhang and 72 inches to the bottom of the window. And this is a right angle triangle, and we don't have another angle. That's what we're trying to determine right now. So angle A is what we're after. So this uses the tan function again, and so our formula is tan A is opposite over adjacent, 72 over 48. Tan A is equal to 1.5, and then in your scientific calculator you type in tan negative, that's the thing on the calculator, and you end up with angle A is 56 degrees, okay? So at 56 degree angle, my window is going to be completely shaded, no sun coming in. And then you go to your sun app and you can figure out at what day of the year is 56 degrees the sun angle. And for me, May the 10th. Now where I live, you have to be observant about where you live, but we can't even put our garden in outside May the 10th. It's like the third week in May is when we put our garden in outside. So it's nice outside, but it'll still have a little bit of a risk of frost at night. And I don't really need any heating. I don't want my house heating up outside. So it's actually perfect that I can fully protect my glazing from any additional heat on May the 10th. So we got full sun when it's cold out, and no sun when it gets warm enough outside that it's actually time to start thinking about cooling a building. But you don't need to cool a building because you don't have the sun heat coming into your building. Now in a passive solar house, there is actually a percentage of glazing. You don't want full glazing because what that will do is overheat your house during the day, and then you'll have more heat loss at night. So there's actually a formula. It's kind of called the 7% rule for amount of glazing versus square foot on the interior of the building. So you don't want too much glazing, you don't want too little glazing. Where I live, it's one of the sunniest places in Canada, 319 sunny days per year on average. If you live in a place that doesn't get much sun, you might do some adjustments. For me, if it's a partial overcast or partial sunny day, I'm still picking up heat for my house, and there's no issue. If it's a snowstorm, heavy overcast, you're not going to pick up very much heat on those few days. So a little bit of a wood stove backup if you want, or something like that. But this works for almost all the time. Now, my house is small. The property tax is very high, and it costs a lot to build a really well-insulated, efficient house. But my house, we still have to use a little air conditioner, and it has the tiniest furnace we could get in it. It barely uses any gas, really. But our house doesn't have a lot of thermal mass air and just stuff in it. My house, because it's built properly, if it was 10 times the size, it would actually eliminate our need for an air conditioner and eliminate our need for a furnace just to get up to comfortable t-shirt weather. So contrary to popular belief, the bigger the building, as long as it's well insulated, designed properly, situated to the sun properly, and all of these calculations and factors, a bigger building works better than a smaller building. My kids going in and out in the summertime 400 times. It's exchanging the air, and then my little house will warm up kind of because of that. It's not warming up because of the sun. It's warming up because there's not much air in there, and all the air exchanges. So if you're thinking, how do I retrofit my house to be passive solar? Well, you can't really, right? Most houses are not facing the right way. There's no thought process to where the sun is. Nobody cares about natural heating with this technology. So if you can find somebody that still is oblivious to this information, you can sell your house and then build a proper one. They're so few and far between, they're almost non-existent to find one situated properly on the planet that you can purchase. So you kind of have to build a new one. But in the off chance you have a retrofit thing, maybe your house has a few south windows, and you notice in the summertime, holy cow, it's hot, and you notice your air conditioning bill is high. Well, you can build a little pergola sun protector thing, the right height above the window and the right length out on a south window to protect the summer sun from heating up your house. So I did that on one of my west windows, because on the south it's protected from the truss, but I have a west window that I wanted to protect from the sun coming in on the west, kind of in the late afternoon. So you can do minor retrofits like that, but essentially, again, over 99% of all buildings aren't faced the right way. Cities aren't built to have free heat and light and no cooling and no heating. They're built really, really stupidly, right? If I was a city planner, I would have roads running east to west and enough space that one house could have passive solar against the street and the next one on the alley or something. You know, it's doable, but, I can't fix all the world's problems, so that's why I do things for myself. But this is for a passive solar building. A greenhouse is different because plants need light. Let me show you how that works. Okay, so for my greenhouse, or any greenhouse, like deep winter greenhouse like I built, this is how I calculated the angles. So here's a cross-section of my greenhouse. Again, it's facing directly south. The sun is over there. Winter sun on the solstice comes in at 14 degrees, way deep into the deep winter greenhouse, hence the name. Summer solstice. In my greenhouse, if you're a follower, it's essentially a little over half of my raised bed is full sun, and then this is shaded. This is where all my thermal mass is. So concrete, water tanks, things like that. In the summertime, I can grow things that don't want direct sun, so lettuces and spinaches and things do good. And the greenhouse is actually cooler back here in the shade. in the summertime than it is outside. But this is calculated different from a passive solar house. Passive solar house isn't for growing plants at optimum efficiency. Passive solar greenhouse, this is all glazing. So we have to deal with more heat gain during the day at all times of the year, and more heat loss at night. So this is all super insulated, and this is the glazing. But plants want as much light as I can possibly give them, right? You can only put so much glazing because you'll block out too much light for the plants. But anyways, talking about angles. This front angle is pretty much irrelevant with polycarbonate. I did this for function. 45-degree angle, ease of construction, and in the summertime I get all this full sun and all this not full sun but still natural light for growing. And then in the wintertime it's blasted all full sun in there. So this is kind of irrelevant. It doesn't do any shading. The shading function of the greenhouse starts at the beam. Now I didn't put a beam and the trusses on top because then I have a beam that would shade. So I hung my roof system off of a beam with big hangers, so I didn't have any shading from a beam, right? But anyways, what do we know? We know the angles, so 14 degrees or 61 degrees in the solstices. So let's talk about the deep winter aspect of it, 14 degrees. So we know that angle, we have to make ourselves a triangle, and let's just do a guess and check. This is what my greenhouse is. It's 32 feet from the post to the back wall, okay? So we know angle on a right angle triangle, meaning we know the angles, and we need one side, so let's do 32 feet. So tan 14 degrees is equal to opposite over adjacent, so x over 32. Do that and you end up with x is equal to 8. So this side of the triangle is 8. So my post from the concrete, finished concrete, to the underside, like where the shading function starts, is 15 feet. So in our triangle that we made here to utilize that 14-degree winter angle, it's 15 feet minus the 8 feet that we came out with is equal to 7 feet up the back wall is where my sun is. So the top, my back wall here, I did 11 foot 3 inches after concrete it worked out to. So the top 4 foot 3 inches exactly is always shaded. So the lowest sun part of the year, the top 4 foot 3 inches, and that is where I put my water tanks on pallet racking. Now, if you wanted to change up my design a little bit, you could do the back wall exactly 7 feet from the concrete, and then the sun would be exactly with the roof. Or you could have even, and I had thought about this, I didn't do it for a variety of reasons. I wanted the shading thing up there and the height, but you could essentially do the roof exactly like that, or at a lower angle so the sun would come and actually reflect the roof light down if you wanted. Now, if you are in a different part of the world, so further south than us, so 14-degree winter solstice is very low. So if you're in, I don't know, Montana, North Dakota, Arizona, you know, your winter sun is much higher. So you wouldn't go as deep. You wouldn't have a deep winter greenhouse. Maybe you'd adjust mine. This works for me. Maybe your back wall would be here, or you could raise this up more and have a bigger angle. Something like that, because your sun isn't going to come in as deep. Your sun in the winter solstice would be like this. So you can make adjustments based on your geographical location, but this is how I calculated that. So again, the front is irrelevant with polycarbonate. If you're using glass reflects the light. So if I was using glass and they didn't invent polycarbonate, which refracts light, but then it would just be a winter use greenhouse. It wouldn't serve much purpose in the summer, but I would do perpendicular to the winter solstice, so 14 degrees. so it drives directly perpendicular into glass. Now, if you just want a greenhouse, you're not going to use it at all in the summertime and just the winter time, you would do it like this. So you'd have way less full sun in the summertime, but it would just be winter use. So this would mean less heat loss, because I have more heat loss, heat rises here, and slightly less surface area of the glazing for heat to lose. You could actually even, we're so far north, if you just wanted something just for winter, I wouldn't even do this 14 degrees probably. I'd just do a wall like that, and you could use the greenhouse all winter, but summertime comes around and you'd only have this in full sun, this little bit, but I wanted the function of it too in it. For the little tiny bit extra glazing, but for the amount of space I got, this I figured was worth it, and I was right about that. Okay, so that's calculating greenhouses. It all comes down to trigonomic functions, cosine, tan, right angle triangles. You can literally figure out anything you want to with the sun angles. This is another really easy way that you can find your calculations, to do quick calculations so you can kind of guess and check on whatever project you're doing. But we're essentially looking for rise over run, okay, at our angles that we need. So tan 14, so that's my winter solstice when the sun is lowest, and do a rise of just 1. So I'm looking for a ratio. So just type 1 in the calculation, and we're looking for the adjacent side of our thing. You run it through the function tan 14, plug it in the scientific calculator, is 0.2493 is equal to opposite over adjacent, so 1 over x we're trying to find. So x is equal to 1 over that, and x is equal to 4. So we found out that our ratio, our rise over run, is 1 to 4. So that means if I have a 1 foot pencil and the winter solstice, 4 feet of shading behind that pencil. We can calculate this super quickly for any angle. So our summer solstice, where I live, is 61 degrees. So tan 61 is equal to 1.8. Type it in the scientific calculator. So 1.8 is equal to opposite over adjacent. So this equals x is equal to 0.55. So that means if you have a 1 foot pencil, it's going to do essentially a half a foot of shading behind your pencil. And this can help you out for more quicker calculations. So it's like, well, if I build a pergola at 2 feet, how much shading am I going to have in the summer and the winter? And you can more quickly find that if you use the trigonometry and your angles to find your ratios. And then guessing and checking is quite a bit faster. Once you think you have it perfect, then go back, type in your actual calculations and measurements from what you know, and get the exact measurements that you need to make the optimum passive solar house, building, chicken coop, greenhouse, everything. The sun's a powerful thing. It's completely free over there. You don't need heating and you don't need cooling, or you can reduce it drastically. We still use a tiny bit of natural gas. For the amount of stuff that we have, our bill would probably be 10 times what it is if we didn't have passive, or if I didn't build everything super insulated, designed properly to the sun. It's awesome. I love it. It's my favorite thing. This is my favorite thing. So nerd alert, but fun stuff. Is this thing on? Arcopia the science guy.